Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Picture this. It's September 2023.
Right.
You are just going about your normal day, maybe pouring a cup of coffee, sitting in traffic, just taking a breath.
A completely ordinary Tuesday.
Exactly. But right at that exact moment, high above our heads, NASA's Fermi satellite registers an event in the cosmos so staggeringly powerful that for a brief, just a fleeting fraction of a second, a single explosion outshines entire galaxies.
It's almost hard to wrap your head around the scale of it.
It really is. We are talking about a concentrated burst of light that dwarfs the combined output of billions of stars.
Billions, yeah.
And it gets registered in the astronomical community as GRB 230906A.
Which is a highly peculiar, immensely violent class of phenomena.
Right, a short gamma-ray burst.
Wow.
So, okay, let's unpack this. Because trying to mentally process an explosion that outshines a galaxy, it requires looking at the actual mechanics of what triggers it.
And the culprits in this case were two neutron stars.
Dead, crushed remnants of massive stars.
Exactly. Stars that spiraled together and collided hundreds of millions of years ago.
We are going to map out exactly how an explosion of that magnitude happens. But more importantly, we're going to look at how this distant, chaotic violence is fundamentally connected to the jewelry you wear.
And the iron and the blood flowing through your veins right now.
Yeah. So just starting with the sheer physics of what the Fermi satellite recorded that day.
It really challenges our everyday understanding of scale. I mean, to get a blast that outshines a galaxy, you need a mechanism that converts mass into energy with terrifying efficiency.
Right. And that is where the neutron stars come in.
Because we aren't talking about active fusing stars like our sun. We are looking at the absolute extreme limit of material density.
The very limit before black hole forms.
Precisely. When a giant star dies and its core collapses, the gravitational crush is so intense that electrons and protons are physically forced together.
They just get mashed into neutrons.
Well, mashed together to become neutrons, and the result is a sphere maybe 10 or 12 miles across.
Basically the size of a small city.
A small city, yeah.
Yeah.
But it contains the mass of an entire sun.
Which is wild. Like a single teaspoon of neutron star material would weigh, what, billions of tons?
Billions of tons. Just one teaspoon. So hundreds of millions of years ago, two of these ultra-dense remnants found themselves locked in a decaying orbit.
Just circling each other.
Circling, spiraling toward each other, accelerating to a significant fraction of the speed of light.
Until they ultimately collided.
And that kinetic impact and the resulting instantaneous release of high-energy radiation that is what washed over the Fermi satellite in 2023.
Just visualizing a city-sized atomic nucleus crashing into another one at near light speed.
It is the ultimate cosmic hammer and anvil.
Yeah, that's a perfect way to put it. But the blast didn't happen in a vacuum, which brings us to the actual location of the collision.
The cosmic crime scene, so to speak.
Right, the cosmic crime scene. Because this wasn't some localized event in our own galactic backyard.
Not at all.
The environment where this happened is a faint galaxy situated inside a much larger group of galaxies, and it's a staggering 8.5 billion light years away from us.
The 8.5 billion year travel time provides really essential context here. Because, think about it, the Earth itself is only about 4.5 billion years old.
So this light was already on its way.
The high-energy photons from this gamma-ray burst had already been traveling through the void of space for 4 billion years before our solar system even coalesced from a cloud of dust.
Before there was even an Earth to eventually hit.
Exactly. But locating an event that far back in time and that far away in space is an incredibly difficult piece of astronomical detective work.
Because Fermi just gives you the general area, right?
Right. Fermi is a fantastic instrument for detecting gamma rays. But gamma rays are notoriously hard to focus. They don't bounce off traditional mirrors.
They just blast straight through her.
They blast straight through. So Fermi can tell us that a massive burst happened, and it can give us a general patch of sky.
But it can't pinpoint the exact street address.
No, it's too wide of a net.
It's kind of like hearing a sonic boom.
Oh, that's a great analogy.
You know, a jet just broke the sound barrier somewhere overhead, but you can't point to the exact cubic meter of air it happened in just by the sound alone. You have to look for the contrail.
That is exactly it. And finding that cosmic contrail required bringing in two vastly different observational tools.
NASA's Chandra X-ray Observatory and the Hubble Space Telescope.
Right. Now, Hubble operates heavily in the visible and near-infrared spectrum. It excels at showing us the architecture of the universe.
The shapes and structures of the galaxies themselves.
Yes. But to connect the gamma-ray burst to a specific galaxy, astronomers needed Chandra.
Because of the afterglow.
Precisely. After the initial gamma-ray flash subsides, the explosion leaves behind a feeding afterglow of lower energy light, particularly X-rays.
And astronomy professor Jane Charlton highlighted a really critical reality about this specific observation.
She did.
She said that without the incredibly precise X-ray imaging capabilities of the Chandra Observatory, this faint host galaxy would have been completely missed.
Because without the X-ray data, you just have a picture of thousands of distant galaxies from Hubble.
Just a sea of smudges.
A sea of smudges, and absolutely no way to know which one hosted the explosion. You need Chandra to find the glowing embers.
To narrow it down.
Right. What's fascinating here is how relying on a single observational method leaves you blind to the actual mechanics of the universe.
You need the layered approach.
Exactly. By layering the data, taking the high-energy X-ray pinpoint from Chandra and overlaying it onto the deep optical field captured by Hubble astronomers could drop a literal pin on a map 8.5 billion light-years away.
They found the host galaxy.
We found it. But more importantly, Hubble's optical data revealed that this galaxy wasn't just sitting in isolation.
It belongs to a larger group.
It does. And that entire group is currently in the middle of a massive, chaotic cosmic merger.
A galactic pileup. Which is wild because when we think of galaxies, we usually picture these serene, majestic pinwheels just slowly rotating in the dark.
Like our own Milky Way looks in artistic renderings.
Right. But the environment where this burst happened is the total opposite of serene. These galaxies are actively colliding.
Their gravitational fields are interacting in real time.
They are ripping material away from each other, and all that turbulence is stirring up massive, massive amounts of new star formation.
And within this chaotic wreckage, astronomers isolated the exact location of the blast.
Inside a structure known as a tidal tail.
A tidal tail, yes.
So walk us through what a tidal tail actually is, physically, in the middle of a multi-galaxy merger.
To understand a tidal tail, we really have to look at the fluid mechanics of gravity on a massive scale. Galaxies, you have to remember, are predominantly empty space.
Just populated by billions of stars.
Stars and vast reservoirs of cold gas and dust. So when two galaxies pass close to one another, they don't usually crash like solid objects.
They don't just smash together like rocks.
No. Instead, their gravitational fields interlock. But gravity follows the inverse square law.
Meaning its strength drops off exponentially with distance.
Exactly. So the side of a galaxy that is closest to the intruding galaxy feels a vastly stronger gravitational pull than the side facing away.
It's a differential pull.
Differential pull, yes.
It's like taking two massive balls of taffy and bringing them close together. The edges closest to each other grab on, and as the bodies continue their momentum, those edges get stretched out into long, stringy lines of sugar connecting the two main pieces.
That is a brilliant way to visualize it.
Only in this case, the taffy is made of millions of stars and interstellar gas, and the strings are hundreds of thousands of light years long.
The taffy analogy perfectly captures the sheer stretching force involved. That differential gravitational pull literally strips the outer layers of the galaxies away.
It just peels it off.
Peels it off, drawing out these immense sweeping ribbons of material into intergalactic space. Those ribbons are the tidal tails.
The elongated shrapnel of a galactic interaction.
And importantly, those tails are absolutely packed with the cold gas and dust that was formerly just floating in the outer disks of the galaxies.
It gets yanked out and funneled.
Funneled into these narrow streams. And as it does, the gas violently compresses.
And when you compress cold gas in space, you basically build a cosmic pressure cooker.
You certainly do.
The density spikes, the temperature rises, and you trigger a massive wave of new star formation. Which brings us to a specific sequence of events proposed by researcher Simone de Chiara.
De Chiara's timeline is fascinating.
Yeah, he laid out this 700 million year timeline that connects the grand macro scale of this galaxy collision directly down to the micro scale of those two neutron stars colliding.
The timeline he outlines is a perfect demonstration of stellar evolution, accelerated by a chaotic environment.
So the clock starts roughly 700 million years before the gamma-ray burst.
Right. The galaxies get emerged, the tidal forces stretch out the taffy, and the resulting compression in the tidal tail triggers a starburst phase.
Just a massive ignition.
Millions of new stars ignite almost simultaneously within this ribbon of debris. But the key here is the type of stars being born.
The compression favors a specific kind.
The intense compression in a tidal tail heavily favors the creation of incredibly massive stars. We are talking O-type and B-type stars that are dozens of times more massive than our sun.
And the rule with stars is the bigger they are, the harder they fall.
And the faster they burn through their fuel.
Right. A star like our sun might sip its hydrogen for 10 billion years, but these massive giants born in the tidal tail, they are burning through their nuclear fuel at a ridiculous rate.
They live fast and die young. Astronomically speaking, their lifespans are mere blips.
Just a few million years.
Within a few million years, these hypermassive stars exhaust the hydrogen in their cores. The outward pressure of nuclear fusion drops.
And gravity takes over.
The star can no longer support its own immense weight against the crush of gravity. The core collapses in a fraction of a second.
And the outer layers rebound in a catastrophic supernova explosion,
leaving behind the crushed neutron star core we discussed earlier. Now, because stars often form in pairs.
Binary systems.
Yes, binary systems. You frequently end up with two massive stars orbiting each other that both go supernova.
Assuming the explosions don't just kick them apart entirely.
Exactly. Assuming they stay gravitationally bound, you are left with a compact binary system.
Two dead neutron stars orbiting a common center of mass, just floating inside this tidal tail.
Orbiting in the dark.
So the tidal tail essentially acts as a hyper-efficient factory for producing pairs of dead neutron stars.
A factory built from galactic wreckage.
But they don't just immediately crash into each other. According to Dickiara's timeline, they spend hundreds of millions of years in a kind of agonizingly slow death spiral.
Right.
How does a binary pair of dead stars eventually close the distance? I mean, in a vacuum, shouldn't they just orbit forever?
If we relied strictly on Newtonian physics, they would orbit forever. But in the realm of extreme gravity, Einstein's general relativity takes over.
Okay.
As these two incredibly dense masses orbit each other, they accelerate through the gravitational field, which creates ripples in the actual fabric of spacetime.
Gravitational waves.
Yes, gravitational waves. You can think of gravitational waves as a mechanism that physically bleeds kinetic energy away from the binary system.
Like friction, almost.
Sort of, yes. As energy is radiated away into space, the orbit shrinks. It is a slow, relentless process.
So for hundreds of millions of years, they bleed energy.
Spiraling closer and closer, faster and faster, until the orbit decays completely.
And that is the climax of the 700 million year journey. The compact binary star merger.
You touch.
The system violently shears apart, and it triggers the massive short gamma-ray burst that Fermi saw in 2023.
If we connect this to the bigger picture, Dickiara's hypothesis really redefines how we view the life cycle of a galaxy.
How so?
Well, the tidal interactions aren't merely the setting for this event. The gravitational disruption is the direct trigger.
It's a chain reaction.
Exactly. The chaotic merger forces the compression. The compression forces the massive star birth. The massive stars rapidly die to leave neutron stars, and the neutron stars decay into a catastrophic merger.
The largest structures in the universe, colliding galaxies, are directly responsible for generating the most concentrated, microscopic points of extreme energy.
It is the ultimate cosmic domino effect.
That is just incredible. But the final massive explosion, the merger, it doesn't just produce a blinding flash of light and then fade into history.
No, it leaves a very permanent mark.
That collision fundamentally alters the chemistry of the universe around it, because when those two neutron stars slam together, the physics get so extreme that they create a phenomenon called a kilonova.
A kilonova, yes.
And a kilonova is basically the universe's premier heavy metal forge.
The term forge is incredibly accurate there. When we observe kilonova emissions, we are seeing the brightly glowing, rapidly expanding halo of radioactive material ejected during the collision.
Just blasting outward.
And to understand why this is a forge, we have to look at how elements are created in the first place.
Like in normal stars.
Right. Normal stars synthesize light elements, hydrogen into helium, helium into carbon, oxygen, all the way up to iron.
But iron is the wall, right? The dead end.
Iron is the absolute limit for normal stellar fusion. Fusing iron requires more energy than it releases, so a normal star just stops there.
So to get past iron to create elements heavier than iron, like gold, platinum, or uranium, You need something way more intense.
You need an environment with an overwhelming abundance of free neutrons and incomprehensible energy.
Because neutrons have no electrical charge.
Exactly.
If you try to mash two positively charged atomic nuclei together, they just repel each other. But a neutron can just slip right past the defenses and bury itself in the nucleus.
That is the core mechanism of what astrophysicists call the rapid neutron capture process.
The R process.
The R process.
Yeah.
During the fraction of a second when the two neutron stars collide, the environment is flooded with a density of free neutrons that exists almost nowhere else in the universe.
Just a total deluge of neutrons.
Atomic nuclei are bombarded with these neutrons so rapidly that they capture them before they even have a chance to undergo radioactive decay.
So the nucleus just balloons in size.
It balloons, becomes highly unstable, and then finally decays into a stable, incredibly heavy element.
And the kilonova is the site of this R process.
The explosion creates elements like gold and platinum, and the kinetic force of the blast physically scatters them outward into the surrounding interstellar medium.
Which actually solves a massive puzzle in astronomy, too.
It really does.
Because for years, astronomers looking at interacting galaxies noticed something strange. They were seeing heightened levels of heavy elements like gold and platinum, specifically located in the halos, the chaotic outer fringes of these merging galaxies.
And it didn't make sense.
Right. Why is the heavy stuff floating way out in the cosmic suburbs?
Exactly. And the observation of GRB 230906A within a tidal tail provides a highly elegant, observable solution to that mystery.
It's the smoking gun.
It is. The interacting galaxies draw out the tidal tails into the outer halos. The tails greet the massive stars. The stars leave the neutron binaries. The binaries merge in a kilonova.
And their R process sprays those newly forged heavy elements directly into that outer galactic envelope.
The environment forces the creation of the forge exactly where we see the resulting metals.
Here's where it gets really interesting, because we've been talking about galaxies 8.5 billion light years away. But this cosmic alchemy is intimately tied to you, the listener.
Very intimately tied.
Professor Jane Charlton reviewed the data from this event and noted that it gives us a rare glimpse into how destruction acts as a catalyst for creation.
The universe doesn't just destroy. It aggressively recycles.
Aggressively recycles. I love that.
The recycling process is really the foundation of our physical reality. We tend to view massive cosmic explosions as endpoints, the death of stars.
Right, game over.
But chemically speaking, they are seeding mechanisms.
Think about the gold right here on Earth. Like if you are wearing a gold ring right now, or just holding a smartphone that relies on trace amounts of gold in its microchips.
The Earth didn't make that gold.
No. And our sun cannot make that gold. Every single atom of gold on this planet was forged in the rare process of a kilonova.
Which is astonishing to think about.
Billions of years ago, somewhere in the cosmos, neutron stars smashed into each other. And the shrapnel from that distant violence eventually drifted into the cloud of gas that formed our solar system.
You are interacting with the wreckage of a cosmic collision on a daily basis.
And it goes deeper than the metal in your phone. It goes straight into your biology.
Yes. Charlton made a point to connect this astrophysical process to the very physiological mechanisms keeping us alive.
The heavier elements in our bodies.
Particularly iron. Iron has an extraordinary origin. It is the central atom in the heme group of hemoglobin.
The protein in red blood cells that binds to oxygen.
Exactly. When you take a breath, oxygen from your lungs binds to the iron in your blood to be transported to every cell in your body. Without that specific atomic structure, respiration as we know it completely fails.
And the origin of that iron.
It was synthesized in the cores of dying massive stars just before they went supernova. The current estimate is that the iron coursing through your veins right now is an amalgamation of material forged in the explosive deaths of roughly 10,000 different massive stars in the Milky Way's history.
The human body is essentially a mosaic constructed from the remains of 10,000 dead stars.
It is.
Every time your heart pumps, you are relying on heavy elements that were forged in a pressure cooker billions of years before Earth even existed.
10,000 stars had to live, burn fiercely, and detonate violently just to seed the gas cloud that would eventually allow you to exist.
It completely reframes how you look at the night sky. It's not just an empty void with pretty lights. It is the active machinery that manufactured the chemistry required for complex life.
And the timescale required for that machinery to operate is deeply humbling. The universe operates with a profound patience.
Hundreds of millions of years.
Just for the initial galaxies to interact. Then it took millions of years for the massive stars to form and die. Hundreds of millions more for the neutron binaries to decay and merge, scattering their payload.
Just a slow, methodical process.
Then it took billions of years for that scattered stardust, the iron, the gold, the carbon, to coalesce in the interstellar medium, collapse into a protoplanetary disk, and form the Earth.
And then billions of years of biological evolution on top of that.
For organisms to develop the complex metabolic pathways to actually utilize that iron for respiration, we are the beneficiaries of a supply chain that has been running for billions of years.
But even with all of these profound connections and everything we have deduced from the light of GRB 230906A, the cosmos isn't handing over all its secrets.
No, it never does.
There is still a significant amount of ambiguity surrounding this specific event. The detective work is far from over.
The nature of observational astronomy is that every answer refines our models, but it also exposes the limitations of our current instruments.
And in the case of this specific burst, the most pressing unsolved mystery is its exact redshift.
Which translates to its exact distance.
Right. Our current spectroscopic data places it at an estimated 8.5 billion light-years away. But the host galaxy is so incredibly faint, and the data is noisy enough that there is a margin of error.
A fairly significant one.
Because redshift is essentially how we measure distance in an expanding universe, right?
That's right.
As light travels toward us over billions of years, the actual fabric of space is stretching, which stretches the light waves, shifting them toward the red end of the spectrum.
The redder the light, the farther it traveled.
But if a galaxy is barely a smudge on Hubble's lens, getting a clean read on that stretched light is really tough. And if the current estimates are off, this explosion might be even further away than we think.
Precisely. If the actual redshift is on the higher end of the possible spectrum, it would significantly push back the distance in the timeline,
making it much older.
It would make GRB 230906A one of the most distant and therefore one of the earliest short gamma-ray bursts ever recorded in human history.
Meaning we're looking at the R-process heavy element forge operating incredibly early in the universe's lifespan.
Which raises an important question about the future of our observational infrastructure.
Well,
we've pushed Chandra and Hubble to their absolute limits to find this one bullet hole.
We need better eyes.
Exactly. While Chandra and Hubble have defined a generation of astrophysics, they simply cannot resolve the faint spectroscopic signatures of galaxies at the very edge of the observable universe with the precision we now require.
So what's the next step?
To lock down the true distance of this burst and to deeply map the tidal structures of these ancient galactic mergers, we are entirely dependent on next-generation observatories.
Like the James Webb Space Telescope.
Instruments operating with the infrared sensitivity of JWST, combined with proposed future high-energy X-ray probes, will be required to really dissect the chemistry of these distant, chaotic environments.
We are always building a bigger lens to see a little deeper into the dark.
Always.
But here is the ultimate twist to this entire story. We've been looking outward this whole time, studying this chaotic galactic merger 8.5 billion light-years away, analyzing the tidal tails and the kilonova forges.
Right.
But the physics we are observing out there are eventually coming for us.
Yes, they are.
Professor Charlton reminded us of a very sobering fact. Having neighbors in the universe is common. Galaxies are highly social. They cluster.
And our own Milky Way Galaxy has a very massive neighbor.
The Andromeda Galaxy.
It is the closest major spiral galaxy to our own, located approximately 2.5 million light-years away.
Which seems far, but on a cosmic scale, it's right next door.
It's right next door.
Oh.
If you look at it in the night sky today, it appears as a faint, stable smudge of light. But the gravitational dynamics between the Milky Way and Andromeda are already locked in.
The gears are turning.
The two galaxies are gravitationally bound, and they are currently accelerating toward one another.
The space between us is shrinking every second.
As Charlton pointed out, living in a galactic group is standard. But undergoing a major merger is a completely transformative event. And for the Milky Way, that event is an absolute certainty.
It is a cosmic inevitability. In roughly 4 to 5 billion years, the Milky Way and Andromeda are going to collide.
And, as we've learned from studying GRB 230906A, galaxies don't just gently bump into each other.
No, they don't. When Andromeda arrives, our serene spiral structure is going to be completely obliterated. The exact same chaotic physics we just mapped out, 8.5 billion light-years away, are going to happen right here in our local space.
The parallels to our future are undeniable.
It's going to be a mess.
A spectacular mess. As the two immense dark matter halos and stellar disks intersect, the differential gravitational forces will tear both galaxies apart.
The night sky from Earth, assuming the Earth still exists in some form, would be totally unrecognizable.
Completely alien. Massive tidal tails will be violently drawn out from the Milky Way and Andromeda, stretching hundreds of thousands of light years into the intergalactic medium.
Just massive ribbons of taffy.
Ribbons of taffy, yes. The interstellar gas within our galaxy will be subjected to immense shock waves and compression.
And we know exactly what happens when you compress gas in a tidal tail. The cosmic pressure cooker turns on.
Exactly.
The Milkometa merger is going to ignite a furious firestorm of new star formation. Millions of massive O-type and B-type stars will burn fast, go supernova, and populate our newly formed tidal tails with a massive new generation of dead neutron stars.
The cycle will repeat itself flawlessly. Over the subsequent hundreds of millions of years, those local binary neutron stars will bleed their orbital energy via gravitational waves.
They will spiral inward.
And eventually, our newly merged galaxy will be lit up by a series of short gamma-ray bursts and kilonova explosions.
Setting off the forge again.
And our process will activate in our own cosmic backyard, heavily enriching the local environment with a massive influx of newly forged heavy elements.
Fresh gold, fresh platinum, fresh iron.
A whole new batch.
So what does this all mean for you? It means that you aren't just a passive observer sitting on a rock in a static universe.
Not at all.
You are an active participant in an incredibly violent, incredibly beautiful cycle of cosmic recycling. The iron currently binding the oxygen in your blood is the direct physical evidence of ancient stellar destruction.
We exist because stars died.
We are walking, talking proof that destruction is the absolute prerequisite for creation. And knowing that our entire galaxy is destined for a cataclysmic collision just proves that the mechanics of the universe never stop.
It is a profound realization that the violent processes we observe in the deepest reaches of space are the exact same processes that engineered our present reality.
And they are the exact same processes that will dictate our distant future.
The universe is a continuous engine of transformation.
And that leads to a thought I want to leave you with, a concept to just sit with and mull over long after you finish listening. We know, as a matter of measurable physics, that the iron pumping through your veins right now was forged in the violent deaths of 10,000 ancient stars.
10,000 stars.
And we know with absolute gravitational certainty that in 4 to 5 billion years, our home, the Milky Way, will be violently torn apart and smashed into Andromeda. The skies will blaze with new star formation, monumental tidal tails will whip across the dark, and an entirely new generation of heavy elements will be forcefully scattered into the void.
Seeding the next generation.
Right. So when our galaxy is finally destroyed and completely remade by that future collision, what entirely new, unfathomable forms of creation, what strange new chemistry, or perhaps even what unimaginable new forms of life might eventually be catalyzed by our own destruction?